Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I'm Siti Maisara as the second speaker from the group 9. I will explain our material about the Arithmatica. But before that, first I will introduce the biography of Diopantus. Diopantus, 250 BC until 200 BC. Diopantus of Alexandria, born probably sometime between AD 201 and 215, died around the age of 84, probably sometime between AD 285 and 299. Diopantus was a Greek mathematician who lived in Alexandria. At the time, Alexandria was a center of learning. Diopantus is also known as the father of algebra. During his lifetime, Diopantus was famous for his work titled Arithmatica. Diopantus is also known as the father of algebra, but now the nickname is being worn by Al-Khwarizmi. During his lifetime, Diopantus was famous for his work entitled Arithmatica. Arithmatica is an entitled discussion of number theory which contain the development of algebra, which is done by making equations. These equations are known as Diophantine equations. Simple form: ax plus by equals c. B is coefficient and c is constanta. The solution to the Diophantine equation is all pair of integer x, y that satisfy this equation. The Diophantine equation is an equation that has Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I'm Siti Maisara as the second speaker from the group 9. I will explain our material about the Arithmatica. But before that, first I will introduce the biography of Diopantus. Diopantus of Alexandria, born probably sometime between AD 201 and 250, died around the age of 84, probably sometime between AD 285 and 299. Diopantus was a Greek mathematician who lived in Alexandria. At the time, Alexandria was a center of learning. Diopantus is also known as the father of algebra, but now the nickname is being worn by Al-Khwarizmi. During his lifetime, Diopantus was famous for his work entitled Arithmatica. Arithmetic is an analytical discussion of number theory which contain the development of algebra, which is done by making equations. These equations are known as Diophantine equations. Simple form is ax plus by equals c. B is a coefficient and c is constanta. The solution to the Diophantine equation is a pair of integers x, y that satisfy this equation. The Diopantus equation is an equation that has. Next is Diopantus number theory. From the time of the discovery of irrational number, Greek mathematics had veered away from the purely arithmetical approach. One result was the all algebraic problems, even to the solution of a simple equation, whereas in Combs and its exable geometric mold. With Diopantus next to Pappus, the last great mathematician of classical antiquity, come an emancipation of algebra. Practical nothing is known of Diopantus as an individual, save that he lived in Alexandria about the years 250. Although his works were written in Greek and he displayed the Greek genius for theoretical abstraction, Diopantus was most likely a Hellenized Babylonian. What personal particular we have of his career come from the wording of the epigram problem. His boyhood lasts for 1/6 of his life. His birth grew after 1/12 more. After more he married, and his son was born 5 years later, and son lived to half his father's age, and the father died 4 years after his son. If x was the age at which Diopantus died, the equation becomes x equal x/6 plus x/12 plus x/7 plus 5 plus x/2 plus 4. And he must have reached an age of x equal 84. But it 1 year of or often in 1 century is not certain. The great work on which the reputation of Diopantus rests in his Arithmatica, which may be described as the earliest theories devoted to algebra. Only 6 books out of the original 13 have been present. The missing books were apparently lost at a very early date, probably before the 10th century, for there is no indication that the Arab ever possessed them. Like the Rhine papyrus, the Arithmatica is an assortment of individual problems, 189 in all. With their solution, the apparent object was to teach the method of solution of certain problem in which it is required to second rational number satisfying specified condition. The square of the ano was denoted by the symbol, the 2 letters of the word dunamis, meaning power. Similarly, the symbol represents the cube of the ano quantity, coming from the Greek word kubos for cube. For high power, he used the following abbreviating symbols. This symbol for the square indicates x the power of 4. And the next symbol for square cube indicate x the power of 5. And the last symbol for cube cube indicate x the power of 6. And the next is the symbol in mathematics. We can see for symbol addition, subtraction, times, and addition. And the symbol lainnya. The sign for subtraction was the symbol, something like an invert the symbol, and the symbol act as an equal sign connection to side of an equation. Example, the symbol means 13.5 x the power of 3 plus 12. And next example, the symbol like that because Diopantus has no addition symbol in expression containing several terms with different sign, he had to pledge all negative terms together of the sign for subtraction. And next is problems, and the last my material is problems from the Arithmatica. Problem 1, book 1, problem 17. Find four numbers such that when any three of them are add together, their sum is one of four given numbers. Say that given sum are 20, 22, 24, and 27. Let x be the sum of all four numbers. Then the numbers are just x minus 20 and x minus 22, x minus 24, and x minus 27. For instance, if 1 plus 2 plus 3 equal 22, 20, then when 4 is added, the both side of this equation x equal 1, equation 1 plus 2 plus 3 plus 4 equal 20 plus 4, or 4 equal x minus 20. It follows that this equation, and so 3x equal 93 or x equal 31. And the required number are therefore 11, 9, 7, and 4. Problem 2. Book 2, problem 8. Divide a given square number, say 16, into the sum of the two squares. Let one the required square be x the power of 2, then 16 minus x the power of 2 must be equal to a square. Have Diopantus was satisfied to choose a particular instead of a perfect square. In this case, the number 2x minus 4 the power of 2, so that 60 minus x the power of 2 equal 2x minus 2x minus 4 the power of 2. Diopantus' choice of 2x minus 4 the power of 2 was decided to eliminate the constant terms from the foregoing equation. He could just as well have picked 3x minus 4 the power of 2. The result was the equation 5 x the power of 2 equals 16x with positive solution x equal 16 over 5. Therefore 1 square will be 256 the power of over 25, and the other 16 minus 259 over 25 equal 144 over 25. And problem T at book 2 problem 20. Find two numbers such that the square of either add to the other give a square. Diopantus choose the number to be x and 2x plus 1. If these are used, the square of the first plus the second automatically become a square no matter what the value of x, thereby satisfying one condition. X the power of 2 plus 2x plus 1 equal x plus 1 the power of 2. The square of the second number plus the first is 2x plus 1 the power of 2 plus x equal 4 x the power of 2 plus 5x plus 1. To make this expression into a square, Diopantus assume that is will equal 2x minus 2 the power of 2. The effect will be to produce a linear equation in x, which will also happen if one use 2x minus 3 the power of 2 or 2x minus 4 the power of 2 instead of 2x minus 2 the power of 2 the power of 2. Then 4x the power of 2 plus 5x plus 1 equal to x minus 2 the power of 2 equal 4x the power of 2 minus 8x plus 4, leading to the equation 3x equal 3 or x 3 over 13. The desired number are 3 over 13 and 19 over 13. Problem 4, book 2, problem 30. Find a number such that is if two given number, say 6 and 7, are subtracted from it, both remainder are square. Call the number x so that the problem is one of making x minus 6 and x minus 7 into perfect square. Let the equation. Here we see an approach that comes close to a method in Diopantus' work. They use the algebraic identity a the power of 2 minus b the power of 2 equal a plus b times a minus b. The difference a the power of 2 minus b the power of 2 equal x minus 6 minus x minus 7 equal 1 is resolved into two suitable choose factor from which a and b can be obtained if one takes 2.5 as the factor setting. Example, a plus b equal 2 and a minus b equal a half. Then a equal 5 over 4 and b equal 3 over 4. It follows that x minus 6 equal 25 over 16 and x minus 7 equal 9 over 16, which x equal 121 over 16 is the number solved. Problem 5, book 3, problem 70. Find two numbers such that their product A to either 1 or 2, their sum give a square. Call the number in question x and 4x minus 1. Then x times 4x minus 1 plus x equal 4x the power of 2 equal to x the power of 2. So the one condition it satisfies immediately. Now it is also required that each of the expression x times expression this equation and next equation has to be a square. Diopantus method of solution again depend on using the identity. It involves taking the difference between 4x the power of 2 plus 4x minus 1 and 4x the power of 2 plus 3x minus 1, namely x, separating this into the two factor 4x and 1 over 4 and equating one factor with a plus b and the other with a minus b. But a plus b equal 4x and a minus b equal 1 over 4 imply that a equal a half times 4x plus 1 over 4 and b equals half times 4x minus 1 over 4. Thus the equation from either of which equation we arrive at the value x equal 65 over 224. The two numbers are therefore 65 over 224 and 36 over 224. Problem 6 at book 3, problem 21. Divide a given number, for instance 20, in two parts and second a square which addition to either of the part products a square. Let equation 1 and 2 be the two part of 20 and take the x the power of 2 plus 2x plus 1 equal x plus 1 the power of 2 to be the added square. The condition require that each of the expressions first equation positive x the power of 2 plus 2x plus 1 and the second equation x the power of 2 plus 2x plus 1 should be the square. Diopantus observe that when x the power of 2 plus 2x plus 1 was at the to either 2x plus 3 or 4x plus 8, a perfect square result. And the equation 2x plus 3 plus x the power of 2 plus 2x plus 1 equal x plus 2 the power of 2 and 4x plus 8 plus x the power of 2 plus 2x plus 1 equal x plus 3 the power of 2. Taking 2x plus 3 and 4x plus 8 as the two part of 20 gives 6x plus 11 equal to 22, which the two part of 20 are therefore 6 and 40, while the 8 square is 3 over 4 and 25 over 4. There are other possible. Diopantus has called the square to be 8 x the power of 2 and use the relation this equation, and the two record part of 20 will be 68 over 10 and 182 over 10. And the last problem, 7, at book 6, problem 90. Find a right triangle such that its area at to one of its legs give a square and its perimeter is a cube, using the formula for right triangle attribute to Pythagoras. Diopantus called the side 2x plus 1, 2x the power of 2 plus 2x, 2x the power of 2 plus 2x plus 1. The perimeter of the triangle will then be 4x the power of 2 plus 6x and plus 2 equal 2 times 2x plus 1 times x plus 1. It's difficult to make a quadratic cube, and Diopantus noticing that factor x plus 1 in the expression for the perimeter. Consider in turn the triangle 2x plus 1 over x plus 1, 2x and 2x quadrat plus 2x plus 1 over x plus 1, obtained by dividing each of the side by x plus 1. This new triangle would have perimeter 2 times 2x plus 1 and area 2x plus 2 plus h x over x plus 1. Adding the latter value to 2x plus 1 over x plus 2 plus 1, once that the equation and equal, and the last result 2x plus 1. The problem requires x to be chosen so that 2x plus 1 is a square and 2 times 2x plus 1 is a cube, that is ending a cube that is twice a square. The obvious choose is 2 times 2x plus 1 equal 8, or x equal 3 over 2, which leads to the triangle with side 8 over 5, 3 and 70 over 5. I think that's all. Thank you very much.